Hello again, my dear students, and it's now part number 2 with this nano biosensor lecture. If you remember, we have reached the conceptual know-how of making a biosensor, a nano biosensor using organic field effect transistor. And by the end of the previous lecture, we have mentioned that whenever you can visit a huge amount of atoms in literature in order to fabricate or even simulate nanobiosensors, we should have what we can call a evaluation criteria or evaluation parameter to evaluate the performance of our transistors. And as I mentioned earlier, these evaluation parameters for transistors are not only limited to FETs, but we can consider it as a general parameter to describe the macroscopic performance of a transistor. These are the 4 main parameters evaluating or characterizing the performance of an generally transistor, and in our case, we will reflect this typically on FET. So the parameters are the threshold voltage, the on-off current ratio, the subthreshold swing, and the field effect mobility. Let's start with the first term, which is the threshold voltage. I think we already have highlighted the physical meaning of this threshold voltage earlier in this lecture, in the part 1 of this record. When we mentioned that threshold voltage is defined as the minimum gate voltage to be biased in order to make a connection, or what we can call a channel, between the source and the drain. Actually, this is a very debatable part of a design. What is the target value for a threshold voltage? So, in some application, typically in digital electronics, we don't recommend this very low threshold voltage, because with any input voltage on the gate, your transistor can turn on. However, in other applications, like in our case, for example, in biomedical sensors, or in generally in sensors, sometimes it's targeted to have a very low threshold voltage. We sometimes call it an ultra low threshold voltage of it, so that you can turn on your sensor with minimum power requirement. And this is usually an important and a critical target for sensor design. On the other hand, we can demonstrate what's called a depletion transistor. A depletion transistor in general is a transistor with alternating threshold voltage. For example, in an N-channel MOSFET, you should act to have a positive V threshold, because the positive voltage will attract electrons to construct the channel connecting the source to the drain. But in sometimes we can have what we call a depletion N-channel MOSFET, where your threshold voltage is turning to be negative. In this case, you don't need to do any positive voltage. Even the 0 voltage will turn your transistor to be on. So it's turned on by default transistor. Again, it's a debatable matter between being a disadvantage in some application or being a target in another application. Another important parameter is what's called the on-off power current ratio. And this on-off current ratio actually push us toward what's called the sub-threshold region. Generally speaking, my dear students, when we consider an idealistic or an hypothetical characteristic for a transistor, which most likely these characteristics you studied in early electronic courses, we told you that the sub-threshold is neglected, or you can assume that whenever the threshold, the gate voltage is below the threshold voltage, then we can assume a zero current. However, realistically, current should accelerate from an initial zero value to an turning on value in some sort of variation, which we call the subthreshold ratio, or sorry, the subthreshold region. So that's basically mean that whenever you have a transistor with a binding on the gate below the threshold voltage, there is still a current conducted, a drain current conducted in this transistor, which basically means that your power consumption in this case is not typically equals to zero, or what we can call the off power of a transistor. So your target is usually to push this on-off current ratio to be as high as possible. So to have the highest possible current whenever your transistor is turned on, and the lowest possible current whenever the transistor is turned off. As you can see, for example, in this red curve, while monitoring on the on current with respect to the off current. Usually, in order to investigate such characteristics, we need to have a semi-logarithmic characteristic curve showing the drain current in a log scale with respect to the gate voltage, so that you can see in depth what happened in the subthreshold region. A third important parameter is how this acceleration occurs. I mean, the acceleration in the subthreshold region. How your current will intend to move from a zero state to a on state during the subthreshold region. And this is typically what we call the subthreshold swing. Generally speaking, as you can see, it's generally some sort of a derivative or a slope or a derivative of the current with respect to the voltage, as you can see here, while considering an important parameter. I think we will consider it later on 2 or 3 slides from now, which are the capacitance included in a MOSFET or in a transistor in general. So to what extent your transistor will be able to accelerate from the zero current to the on current in a high and speedy way. This what we can call, or this is described by the subthreshold swing. Finally, a very important parameter related to the device mobility. Here, we have to distinguish between the mu term, which is a very familiar term for us from a material point of view as a mobility. I believe all of you know mu n and mu p to express the electron and the whole mobility in a material. But herein, we are not considering the material mobility. We are considering the device mobility. So the capability of the device to transfer current, or what we can see for a given gate voltage, the capability of the device to transfer drain to source current, or IDS. This is represented through the device mobility. And again, you can find some geometrical parameter included, like the length and the width of the channel. And also, again, you can find the capacitance, where we are going to demonstrate in the next slide. But before going further in that, we have to highlight that as our transistors are working in 2 regions of operation, what we call the triad region and what we call the saturation region, then we have to expect that we will generally have 2 mobilities. One in the triad region and the other in the saturation region. In each case, or in each region, you are using this derivative term between the IDS and the VG or the VGS. So using these 4 parameters, we can characterize, or we can have a macroscopic characterization for our device. Of course, besides the general IV characteristic curves, including the ID VDS curve and the ID VGS curves, which are commonly used to express the characteristic behavior of any transistor. Now, as you see from the previous equation, even from this equation you see in this slide, the capacitance of a transistor, or what we can call between brackets, the parasitic capacitance of a transistor, is a very key parameter in design. And you can understand that these capacitance can differ whenever we change the topology or the architecture of the transistor. In our current study, we will start by having this demonstration for a capacitance in a very famous metal oxide semiconductor feed effect transistor, or what we can call the MOSFET. But I think that if you deeply understand the capacitance model here, you will be capable to reflect this capacitance model to any other type of transistors or any other types of semiconductor devices in general, because you are going to reflect the same concept on any structure, whatever the structure is. So what we are going now, my dear students, is we are going to give some focus on the capacitive modeling of our transistors, and then we will answer a very important and critical question: is why this capacitance modeling for our transistor is critical, or in other words, when we should consider such a capacitance modeling in our design. Okay, so let's make a focus on different capacitance that may exist in a MOSFET structure. Generally, in order to detect the capacitance in a structure, you have first to justify why we should have a capacitance. So, generally speaking, the first and the main source of a capacitance is having an non-conducting layer between two conducting layers. This can be in a direct form. For example, in capacitance, in the MOSFET, sorry, we have an oxide, which is a non-conducting material. So this should be a direct source for a capacitance. In some MOSFET, as the one here, we have a non-conducting material above the oxide to extend the oxide, or maybe to influence the K factor of the oxide. So this is another source for a capacitance. So this is a first direct source. However, this is not the only reason of having incapacitors. For example, having a p-n junction is another reason for having a capacitance, because as you know, a p-n junction includes in between what we can call the depletion region, which an indirect form for a region depleted from carriers, or between quotation insulators. So p-n junctions is another region for a capacitance. A third region for a capacitance might be a diffusion capacitance of having two layers of different doping. So having two layers of different doping can include also some sort of a depletion region in the energy bandogram, which well results with the capacitance. So let's see this. Let's start with a very direct form. Here we have two layers of oxide, this oxide and this NC. So these two layers will result with two capacitance. These are direct capacitance, which represents a two metals or two conductors. Here we have a perfect conductor, a metal gate, and here we have an N region material, which is supposedly with a high conductivity, at least in the N side. And in between, we have two types of dielectric materials. That's why we have two types of capacitance here. So this is the direct form of a capacitance. And as the gate oxide layer is extended to include a portion of a source and a portion of a drain, then we will have also a gate source capacitance and a gate drain capacitance, as you can see. This is simply due to this overlapped area extended from the gate oxide to cover some of the source and some of the drain. So these are the first capacitance. Then let's go ahead. Now, this is an N region with the effect of the positive voltage applied to the gate, which turn, or what we can call invert this channel region to be an N type. So this is an N region. And our substrate is a P region because it's a N-channel MOSFET. So we build an N-channel MOSFET on a P substrate, leading to have a PN junction here, creating a very important and critical parameter capacitance in the MOSFET, which we call as a depletion capacitance. Again, we have another PN junctions because our drain is an N and our substrate is a P. So we have a PN junction capacitance here, and we have a PN junction capacitance there. Finally, we have two other types of capacitance. We have a capacitance between the drain, the source and the channel itself, because the level of the doping in the source and the level of the doping in the drain in the channel are not matched. Usually, the source and the drain are with N++ doping, high doping, but the channel is an inverted region with slightly low doping, creating a capacitance here. And finally, we have somehow a diluted effect capacitance, which due to the trapping effect, we call it C-trap here. So these are different capacitance inside the MOSFET. Actually, not all these capacitance contribute equally to the device. Most likely, the oxide capacitance and the depletion capacitance are the most significant capacitance to our device. However, in order to make a general model for a capacitance inside our device, you can refer to this graph here. We have here the non-conducting capacitance, the oxide capacitance, and then we sum all these capacitance in one capacitance. As I just mentioned, the dominating capacitance here is the depletion capacitance, because simply this is the most dominating capacitance across these capacitance in blue. And finally, these two capacitance can couple together to have one capacitance, as you can see. So this can be simply the capacitance model for a MOSFET. So using the same know-how, using the same procedure, you can implement or you can sketch your capacitance model for any device. For example, returning back to the OFET, for example, organic field effect transistor, we can have a similar capacitance model. Maybe this will be one of our practical examples during the tutorial to try to think together how to build a capacitance model for an OFET or generally for any type of transistors. Now, we studied together in this lecture how we can build a transistor to act as a sensor. Typically, we choose the OFET. We study also the capacitance effect in general. We study also the parameter affecting the OFET or affecting the transistor in general as a characteristic parameter in a transistor. But let's turn back to circuits. Now, as we studied, for example, for this lactate example, we understand that by changing the lactate percentage in the blood, which will react to the organic semiconductor acting as an active layer here, this device, which is the OFET, will change its drain current in this ratio. Now, this is not sufficient to build a sensor. We still need what we can call a interfacing circuit so that we can convert this variation in current into a sensible variation in voltage that can be then fed, for example, in an ADC and in our digital converter. So what we are going to do in the next part and the final part of this lecture is to study together how we can build an interfacing circuit for such case. Again, this is just an example. so that you can generalize it to any other model of a transistor later on. Thank you very much, dear students, for your concentration, and looking forward for the third and final part of this lecture.